think I'm recording. Appears to be. Okay. So so these are this is day 5. So these are day 5 units. Okay, so so we know we're talking about, I'm just trying to get to the point. We know we're talking about finding an accumulation. And we know that we can do that by taking the rate of change and watching it literally accumulate underneath that rate of change function, right? And so what we're looking at here is like creating a function from those values. Does that make sense? So I think in your notes we accumulated the region under 2t, right, which ended up being a line, and the regions underneath ended up being triangles. So we didn't even really need to do a Riemann sum because we could use a geometry formula and get an exact answer. Didn't have to approximate. That makes sense? Okay. So the idea then is, at least for 2t, we could find these exact values. We went from 0 to 1, and then we went from 0 to 2, right? And then we went from 0 to 3 and 0 to 4. We could have kept going. We didn't have to start at 0. We could have started somewhere else. But we saw a pattern in the table, right? Those triangles, we started out from 0 to 0, which obviously was 0 because we hadn't swept out any geometric region yet, right? So we looked at those table values, and the table values went 0, 1, 4, 9, 16. And in the notes I said, hey, we recognize that pattern. That's the pattern of x squared, right? And that's kind of nice. I mean, now you can look at any linear function and kind of get an idea of what the accumulation pattern is going to end up being like. It's going to end up being like something squared. And so that was all fine and good and pretty easily recognizable. But then this idea of the fundamental theorem of fundamental theorem of calculus, the idea is that, well, what if we took that accumulation function and differentiated it? And we ended up back where we started. So we recognized that this pattern in the table was x squared. We differentiated x squared, we get 2x back, which is what we started with, except that we have a variable change. Does that make sense? Okay, so that is the fundamental theorem of calculus. It's called the fundamental theorem of calculus part 2. Some of you might be wondering why we're talking about part 2 before we're talking about part 1. And the answer is we could kind of go either way, presenting which one first. So I go this way, presenting part 2 first, because the end result is that if I have an accumulation and I want to differentiate that accumulation, I just get the integrand back. So it's kind of like we have those properties, right, in math, where we can do something and undo it. Like, you know, start at 4, add 3, then subtract 3. 4, right? Start at pi and multiply it by 7, then divide it by 7. You got the pi, right? And you didn't have to know what pi times 7 was to get there. Thank goodness. You don't want to do that kind of multiplying, right? Especially with that calculator. And that's the idea of the fundamental theorem of calculus part 2, is that we can accumulate something and then say, well, really what I want is to differentiate it. And we can get back where we started with that variable change. We got that variable because we created the table in terms of x, right? That x was the upper bound. And so that triangle kept getting bigger and bigger depending upon what our x was. Okay? So far, so good? So the function we're defining through accumulation is the same as recovering the information about that change in the original function. Yeah. Well, like we start, if you notice in your notes, like I'm looking right at the top of the beginning of the notes that you took last night, and we started out with the function 2t, and we graphed that. And in graphing that, because the upper bound was x, then that gave us a function in terms of an x value. Does that make sense? Okay, so the table, you know, the table says g of x, because x, the x value told us where to stop. Does that make sense? It told us how big to make the triangle. We went from 0 to 1. We went from 0 to 0. That didn't make a triangle at all. Went from 0 to 1, made this little tiny triangle. Right? So that x is telling us where to stop. And then we went from 0 to 2, we got a triangle that was bigger. Okay, so now the pattern of 0, 1, 4, 9, 16 that you have in your table from your notes, that pattern is dependent upon variable x. Does that make sense? Because the x value, the left-hand column of that table told us where to stop the shape. And so if we want to make an algebraic expression based off that table, does that make sense? That the right column definitely looks like something square, and it looks like that upper bound square, which is x. Does that make sense? That's how we got the variable change. We said, let's stop at value x. Let's generate all of these values from the fact that we stopped at value x, and let's see a pattern with respect to value x. Okay? It's a really good question you ask, because a lot of times that's really glossed over. And people are, just like you said, people are sitting there going, why did we change variables? Because we generated a table based on that stopping point, and that stopping point was some random location x. Okay. So that being said, then we're gonna, this is the do and undo accumulation. We did something to 2t. We're gonna undo it by differentiating, which we know how to do that. So differentiating x squared gets us, which looks like 2t, except with the variable change. So a lot of times I call this the plop rule. We're just gonna plop the x in what we see. Yeah, exactly, right? We see 2t. We know 2t is the rate of change, right? We're going to accumulate an area underneath it, quote unquote, right, between it and the x-axis. We're going to accumulate that area, and then we're going to see a pattern and differentiate that algebraic expression for that. Okay. And we get right back where we were. So this process of accumulation, which is that integral symbol, that S symbol, and then putting a differentiation in front of it, that process is do and undo, just like addition and subtraction are. Those two processes are do and undo, or multiplication and division. Squaring and square rooting, right? Those sort of things do and undo. And so does accumulation, or we're going to start calling it integration real soon. And differentiation are do and undo processes. Okay. So the idea then is we're still, the idea is that we're still focused on this rate of change. And it's that integrand, it's the 2t. It's that integrand part of that statement. That's the rate of change. So we're still focused on that. We're still saying, I know that when I have a rate of change, I can recover information about the original function, even if I don't know what the original function is. In the notes, we knew that the original function was x squared, because we can see the parts are good. Okay, so this is that do and undo phenomenon. When we differentiate that accumulation, we end up back where we started. So extending number 1 here, that makes the integrand the derivative. Okay, that's what I just got done saying, right? That's in your notes, that's the 2t. The integrand is that thing that's between the integral symbol and the dt. Okay, so I'm just going to say this, and I'm not going to get too far into it because it kind of relates back to Riemann sums. But when we look at 2t dt, that's like looking at f of x delta x. Okay, that's one rectangle, but we've taken the limit, so we've made the rectangle skinny and we've made them infinite in number, and then the delta t goes to dt. It's called a differential. We'll get more into that later. But that 2t dt is like looking at f of x delta x. It's like looking at height and width of a rectangle. So think of the fundamental theorem of calculus. I call it FTC. Part 2, I call it the derivative part, because that's what we're doing. We're differentiating that accumulation. It's another derivative rule. We're going to look at that notation and just say, oh, there's the derivative. And then we're going to just think of the derivative and how we can recover information about the function. Okay. So we're going to look at more complicated solutions now in class. Okay. So any questions before we look at these situations? Okay. So we can complicate. I didn't really use that word. This concept. I guess it's an okay word. Let's make the comparison to our baseline derivative. So we know that this is kind of our baseline here, right? If we differentiate this accumulation, we get what? Well, but we're differentiating it, so we get 2x. So this is why I tend to call this the plop rule, okay? Because we start out with 2t, and I'm going to plop the x right where the t was. I'm going to plop it right there, and we get 2x. Okay, so I've done two things to 2t. I've accumulated the area underneath it, and I've seen a pattern, and then I've differentiated it. And that's what these two notations are. The integration symbol, or the big S, that's the accumulating, that's the drawing and finding the rectangles and filling out the table and seeing the pattern. And then the ddx is do the derivative on x squared. Okay. Now, the really nice thing is that we can do this as long as we pair up these two processes. We can do this and not worry about the actual accumulation aspect at all. Okay, that's the nice thing. Okay, so and I gave you some examples of that in the notes. Yeah, 2 examples of that in the notes. Okay. So let's look at switching the limits of integration. Notice what I've done here. My x is now here, and my number is up here. So a is numeric. For our example, a was 0. And that's important. One, we need to have a constant, and then we need to have a variable limit. So these are in the wrong spots. So what we need to do is we need to switch them, but in switching them, what we've done basically is we've said, if from A to X is making the shape from left to right, then X to A is making the shape backwards, sweeping from right to left. And that is the negative of going forward. It's like reading the graph backwards. Does that make sense? So if we look at this, if going back to my comment about this being f of x delta x, right? If we think about the delta x, if we go from a to x, then our delta x is positive. If we go from x to a, our delta x is negative. So we end up being a negative value. Okay. So that ends up being negative 2x. So the negative sign comes from rearranging the upper and lower limits to where their correct location should be. And then we're just plopping in that variable because we know that we're doing this accumulation differentiation pair of processes. Yeah. Yep, exactly. Yep. If it's not there, then we make sure that we do an appropriate property, and this would be the appropriate property change. So far, so good? Okay. All right, so we're going to complicate it a little more. in example 4, I've got the constant down in the bottom, so that's a good thing. It's there. But the top is now 3x. So let's kind of speculate here. What should we do with the 3x? What did we do with the x up above here? Okay, we what? You replaced the t with the x. So what should we replace the t with here? 3x. Wouldn't that be intuitive? I mean, wouldn't that kind of make sense? Right? Because we're doing accumulation and differentiation, and you're partially correct. Okay? You're partially correct. So let's take a look at what's going on here. Okay, we know this is x squared, right? We saw this from our table. Now notice that this is just accumulation. This is just integrating 2t dt from 0 to x. Okay, so that's just setting up the triangles and setting up the table and seeing the pattern. Okay, well, if that's the case, then if we just accumulate out to 3x, then that's like saying I have 3x quantity squared. Does that make sense? Right? Because this one said basically I have x squared. You know, throw the x into the squared function, throw the upper limit into the squared function. And so I'm going to do the same thing here. I'm going to throw the upper limit into the squared function. That's in fact what's happening. Now, I haven't differentiated yet. Does that make sense? So I'm going to differentiate this, but before I differentiate it, I'm going to get the brackets out of there. What is the derivative of that? 18x, and that is the answer. Okay, that is the answer to this question up here, 18x. Now, if I would have just thrown the 3x in for this value, would I have gotten 18x? That's where we're going next. Because we really don't want to have to do this step. We want to sidestep this. The only way we could do this is because of what we gained from the original notes. Okay, so this is just what you wrote down. So I changed the screen, but I didn't change the information. Okay. So let's talk about this. We know that this is 2, just like you said, 2 times 3x. Right? That's where the t was. We're going to take out the t. We're going to plop in whatever we see in the top bound. We know the real answer is 18x. Do we have 18x? No. What can we do to, how much do we have here? 6x. So what do we need to do to 6x to get to 18x? Multiply by 3. Where did that 3 come from? How is 3x related to 3? It is, isn't it? Isn't 3 the derivative of 3x? Yeah, right. 3x is a line, goes through the origin, slope of 3. Differentiate that. You can think of it as a couple different ways, right? What's the slope? 3. There's the derivative. Never changes. Or it's 3x to the 1. You can do the power rule, bring down the 1. 3 times 1 is 3. X to the 0. That goes away. So this ends up being the derivative of whatever's up here. Now, where have we seen that? It's the chain rule. My outside derivative is going to be my integrand, because that is what's being accumulated and differentiated. My inside derivative is going to be my upper bound. So that is the way of showing a composite function using an accumulation notation. Now, why didn't we have to do that when it was just plain old x? Right. If we have a plain old x up here, we can still do that. We can always do the chain rule. It'll work whenever. But the derivative of x is 1. We would just be multiplying by 1. So there's your 18x. So that's how you get your 18x, is exactly what you're doing down here. So it's still the derivative of the integrand times the derivative of the limit. In other words, outside derivative, inside derivative, because didn't we literally stick 3x into a different function, right? I mean, we literally created a composite. Okay, so that means that if I have a accumulation function and I have a more complicated stopping point, so like for that one that started in the notes, the 2t one, I could have accumulated that up to like x squared, right? In my stopping points would have been 0 and 1 and 4 and 9 and 16. So I would have made these huge triangles each time. And then I could have gotten a different pattern for my accumulation. Bless you. So if we are going to use the fundamental theorem of calculus, we're going to accumulate, we're going to differentiate, we're going to use the integrand at the upper bound times the derivative of the upper bound. So there is your chain rule. Because remember, function f, right? Look at where it is. It's right here. It's already the derivative. A lot of people want to see like a prime of derivative notation there, but you got to remember that f is already a rate of change. So to put a prime up there would be like a rate of change of a rate of change. That makes sense? So so this is your chain rule for the fundamental theorem of calculus. Ready to try this? So let's do this. There's no way you could be able, you could graph this and see a pattern in the table, right? To get that accumulation function. No way. But we do know that I have an accumulation function, and then look at my question. Look at how I'm hiding this. What is the derivative of the accumulation function? Right? I'm hiding it by asking it this way. And that is another way of saying, what is ddx of this? Now, the first big thing that is missing here is a numeric limit. Does that make sense? Right? We should have an a or a 0 or something, and we don't. Okay, that constant is important because, and let me tie it back to this. What happens when we differentiate a constant? It goes away. That's why when one of the bounds is a constant, we only have to worry about the variable, because we are going to end up derivativating. Goodness, bad grammar. We're going to end up taking the derivative anyways. That's why it's so important to have the number there. We don't have a numeric value there, and that's okay. This is what we're going to do. We're going to assume any number between x and x squared. I don't care what it is. Pick a number randomly. I just picked 3. I'm just going to say, hey, 3 is between x and x squared. And that's true, especially if x is 2 and x squared then is 4, right? So, so we pick any constant value. You could even pick 0. It doesn't matter because we're going to end up differentiating anyway, and that's going to go away. Yeah. Nope. Okay, you could pick pi. It wouldn't change the result, because that constant is only represented in the notation. Does that make sense? Because we're going to accumulate and differentiate. So anything, any constant we get, any number we get is going to go away in the differentiation part. So you could use 0. Lots of people love to use 0 just because it's easy, or 1, or pi. Okay, so I'm just going to say, let's pick 3 to be in between. So then I'm going to get this. Does that make sense? I'm going to like make it into 2 statements. It'd be like taking the triangle from 0 to 3 and taking it out to 2, and then from 2 to 3 and sticking them together. Okay? I'm just taking it and making it into 2 sections. All right, so a quick scan. Now I've got a number in both locations, right? I've got a numeric value as one of the limits here. I've got a numeric value as one of the limits here. Which one do I have to rewrite to get the numeric value in the right spot? Okay, half of you said the first one, half of you said the second one. Right, the first one's got to be rewritten. We need the number down here as the lower limit. So we're going to rewrite the first one with the negative sign. Second one's okay. Which one do we need to do the chain rule on? Yep, we need to do the chain rule on this one. Does that make sense? I'm going to pause here to give you some time to write. So this is how I shorten up what I think about as I'm navigating this. Numeric limits are in the right spot. I'm being asked to differentiate an accumulation or differentiate an integral on both ones, so I know it's a plot. So the first one's going to be a straight up plot, and the second one's going to be a plop and chain. So let me repeat that. The first one is going to be, see where the T's used to be? Right? I replaced them with brackets. Just, it helps me in my mind know that something needs to go there. It's going to be a straight up plot. That makes sense? Okay. Don't forget the minus sign out front. The second one is going to be a plop and chain. Plop and chain. Does that make sense? This is very specialized because of the do and undo nature of the questions we're being asked. Accumulate, then differentiate. Add, then subtract. Multiply, then divide. You don't think too much about those. And they shouldn't think too much about this. Okay, start with pi, multiply by 7, now divide by 7. I bet most of you got the answer without thinking about the stuff in between. Right? Accumulate, then differentiate. Plop. Accumulate, then differentiate, plop and chain. Because we have something more complicated than just x. You're okay? Now, let me just say this about what we got. It's messy. You can leave it exactly the way you have it on your paper. A lot of times when they have you do this, like splitting this into two, they're going to specifically pick things so that you are able to add them together into one fraction. It didn't work out this time. So we're just going to leave it like that. Oops. So any question? Oopsies, didn't mean to do that either. Any questions about that? I just realized I don't know how to get rid of this. Do I have to tap on it again? Oh, that doesn't. That doesn't. I'm not sure how to get rid of that now that it popped up. Sorry. Any questions? Okay, so what is the connection between accumulation function and the integrand? What is the integrand? What is the 2t, that little piece in between the integration symbol and the dt? It's the rate of change, or it's the, what's another word for rate of change? Slow. Okay, let's get lower math. Yeah, that's the derivative. Okay, so the integrand is the derivative. This is really wordy, of the accumulation function. Okay. You doing okay? All right, so on these topic questions, it's literally going to ask you to do a plot or a plot and chain, or it's going to say, hey, here's this accumulation function. And I want to know, kind of like the ones in the notes. I want to know, something about the rate of change. Like now I'm drawing a blank. What was the the drone question, right? What's the rate of change in the altitude? Just using that integrand and using that function. Okay, so we've got those topic questions, and we've got some con. And I clicked too many times. There we go. And so you've got time to work on those topic questions first. We get into those. And we had some great conversations here yesterday about our topic questions, so keep those conversations going. Invite in a member of our virtual crowd into those conversations. I'm going to stop recording, but if you have, I'll keep the session live, so if you have questions, let me know.